Today, we are going to talk about one of the unsung heroes of our modern electrical world. It's the inverter. It's this hidden genius that makes things like solar power and electric vehicles even possible. And we're going to break down exactly how this amazing piece of tech works. So, have you ever really thought about it? How does the raw, direct power from a solar panel on your roof get turned into the kind of electricity that runs your TV? Or how does that huge battery in an electric car actually make the wheels spin? Well, the answer to both, it comes down to one brilliant piece of technology. And that technology is, you guessed it, the inverter. Now, at its core, its job sounds pretty simple. It converts direct current, or DC, into alternating current, or AC. Just think of DC as a one-way street for electricity. It's what you get from things like batteries and solar panels. AC, on the other hand, is the two-way oscillating current that our power grid and pretty much all of our home appliances run on. The inverter is that crucial translator between the two. And we're not talking about little tiny gadgets here. This comes from a real-world example built at MIT, a single inverter that can handle 33 kilowatts of power for a motor drive. To put that in perspective, that's enough juice to run multiple households at once. This is serious high-power engineering, and it's absolutely essential for any heavy-duty applications. Okay, but here's where the real challenge comes in. See, just converting DC to AC isn't good enough. You have to create the right kind of AC. The goal, the holy grail, is a perfectly smooth, predictable wave of electricity. And that is much, much harder than it sounds. This is what engineers call the perfect sine wave problem. So the easiest way to make AC power is to just switch the DC on and off, right? But what you get is this clunky, blocky square wave. And trust me, that is dirty power. Those sharp corners are full of nasty electrical noise. Engineers call them harmonics, and they can make motors buzz and overheat. They waste a ton of energy, and they can even fry sensitive electronics. The goal is this beautiful, clean sine wave. That's the pure, efficient power our grid and our motors are actually designed for. So, how in the world do engineers turn that ugly block into a smooth curve? Well, you can actually think of it like sculpting. They came up with these really clever techniques to literally shape the electrical output, chipping away at all the imperfections to get closer and closer to that ideal sine wave. Two of the earliest methods were harmonic elimination and cancellation. You can think of it like noise-canceling headphones, but for electricity. These techniques use these incredibly precisely timed electrical pulses, or sometimes even multiple waveforms layered together, to basically create an opposing force that just cancels out the worst, most jarring parts of that dirty square wave. But the real game changer, the real breakthrough, was when they realized you didn't have to just switch between fully on and fully off. What if you could add intermediate steps? This is the core idea behind what are called multi-level inverters, and it completely changed everything. Here's how it builds up. A simple two-level inverter just gives you that basic blocky square wave we talked about. But a three-level inverter, it adds a middle voltage step, which right away starts to round off those sharp edges. And as you add more and more levels, creating lots of tiny little steps, you can build a waveform that gets incredibly close to a perfect sine wave. Now, of course, there's always a catch, right? This is a classic engineering trade-off. The more levels you add, the more complex and difficult the circuit is to control. But the benefit is huge. You get an incredibly pure output that needs a much smaller and way cheaper filter to clean up that last little bit of roughness. This whole sculpting method is really powerful, but modern electronics gave us an even more elegant solution. Instead of building with more physical steps, engineers started asking, what if we just switched, but incredibly fast? This brings us to the technique that dominates today, pulse width modulation, or PWM. So think about it this way. Instead of making a few large, careful cuts to shape our wave, like a sculpture with a chisel, PWM is more like using a high-speed power sander. It makes thousands of incredibly fast, tiny adjustments every single second. It's a totally different philosophy. You're not building the shape directly, you're creating an average effect that perfectly mimics it. So how does this magic work? It's actually surprisingly simple and elegant. You have two signals. First, there's the sine wave you want to create. We'll call that the command. Second, you have a very fast, repeating triangle wave. That's the carrier. And the rule is dead simple. The output switch is only on when the command wave is higher than the carrier wave. The result is this rapid-fire stream of pulses that get wider where the sine wave is high and narrower where it's low. And here's the magic. The average value of all those tiny pulses, it perfectly traces the ideal sine wave. And MIT professor David Pearl just sums up the crucial point perfectly. He says, all the distortion and stuff you don't like is such high frequency you can filter it off and get rid of it. The genius of PWM is that all the noise, all that electrical garbage from the rapid switching, gets pushed into incredibly high frequencies, so high they become super easy to filter out, leaving you with nothing but the pure, clean power you wanted all along. So why does all this technical wizardry really matter to you and me? Because this ability to perfectly sculpt power is what enables so much of our modern world. Inverters are the silent, absolutely essential workhorses in countless systems we rely on every single day. With solar power, they're converting the DC from the panels into the perfect AC sine wave to match the grid. In electric vehicles, they're the thing turning DC from the battery into the precise AC that gives a motor that insane, instant torque and speed control. They're even in high-end audio amplifiers, efficiently creating powerful, crystal-clear sound. They really are the universal translator for modern electricity. As our world becomes more and more reliant on electricity from batteries and renewables, the role of these power sculptors only gets bigger. You see, the quest for the perfect sine wave is really a quest for near-perfect efficiency, absolute reliability, and a smarter energy future. So you have to wonder, as engineers get even closer to perfection, what entirely new technologies will that flawless power unlock next?